Guess what, folks? We have made it to Euclid Book 2, proposition number 11. But before we begin, which, by the way, this video not only covers the quadratic formula, but also the golden ratio, I wanted to tell you something before we begin. Some people have been getting kind of confused in my last few proofs, and I wanted to tell you this. When Euclid says that there is to be a square on a certain line, what he's meaning is a physical square. See this square right here? On a physical line like this. This is line AB right here. The square on AB will be a physical square. AB will be the length of one of the square sides. B, whatever here, will be another length, so on and so forth. And all four, this length here, this length here, this length here, and this length here, will be exactly the same size. All four sides will be exactly the same length. So that's why you have a square on AB. Now, the next thing I'm going to say is that Euclid will go on to say that there will be a rectangle contained by AB, BC. What he means is that this line AB will be the length of this rectangle, and BC will be the width. Okay, so the rectangle is being contained by lengths of AB and BC. Keep in mind that we're talking about a rectangle here. The AB and DC will be exactly the same length. This will equal this in length. And BC and AD will be exactly the same length. Like this. So BC and AD will be exactly the same length. So a rectangle contained by AB, BC, well, you can also say that this D here is actually C. And you could say here that this C is actually B. So you're going to say twice the length of AB and twice the length of BC contains the area of this rectangle. Alright, hopefully that got rid of all the confusion. Now let's go back to the proof. Euclid wants you to start out this proof with line AB. And then he says he wants you to make a square from point A to point B to point D to point C. That means that the length of AB and the length of BD and the length of DC and the length of DA are all going to be the same length. Alright? Then Euclid says that by Euclid Book 1, proposition number 11, he wants you to bisect line AC at point E. And then he wants you to draw a line from point E to point B. Okay? And if you do, you will automatically see a right-angled triangle. And that triangle will start at point E, go to point A, and go over here to point B. And we know it's a right-angled triangle because this is a square, and every one of the angles of the square are right angles. All right. Thus begins the proof. Now, here's what Euclid wants you to do next. Get ready, folks. He wants you to continue line CA all the way to point F. Well, here's C, here's point A, and it's going to go here. Here's point C, goes to point A, goes all the way over to F. And then he says EF, the length of EF, has to be equal to BE. Well, here's the length of EF, right here, EF, and it is now equal to the length of BE, which is right here. Okay, this length here and this length here are going to be exactly the same size. But that's not enough for Euclid. No siree, Bob. He wants you to draw a square called FH, and it's to be described on line AF. Well, here is AF. And what he's wanting you to do is he wants you to draw a square, and it's going to be square AFGH. So the length of AF is equal to the length of FG, and the length of FG is equal to the length of GH, and the length of GH is equal to the length of HA. Whew. All right. But Euclid's still not done. No siree, Bob. And then he wants you to draw GH all the way to K. Well, here's GH right here, the length of GH, and we're going to draw all the way down here to K. See where point K is right down here? Starts at point G, goes to point H, comes down here to point K. Alright, now you have the figure he wanted you to draw. Now, the first thing Euclid says is that by Euclid Book 2, proposition number 6, that the rectangle contained by CFFA. Well, where is CF? Well, here is C, and here is F. Okay? Here is C, here is F. And FA. Well, where's FA? Well, here is F, and here is A. Okay? Now, the first thing you should have noticed is that because AF is equal in length to FG, then what you basically have here is a rectangle that starts at point C, okay, goes right down here to point C, goes over here to F, goes over here to G, and comes all the way back down here to K. So the rectangle contained by CFFA is going to be the rectangle CFGK. CFGK. That's the rectangle contained by CFFA. Now, what about the square on AE? Because we're going to add the square of AE to that rectangle right there. Well, let's find AE. Well, here is AE. Now, we would draw a square right here. And we could draw it out here, here, here. We'd actually end up having another point. If we drew out that square, we'd have another point right about here. And I'm going to label that M for mystery point. And if we were to connect that, we would have this length equal to this length, equal to this length, equal to this length. Okay? So, the rectangle contained by CFFA plus AE, the square of AE, equals the square on EB. Now, where is EB? Well, here's E, and let's see, B. Okay? So, we would draw a square out way out and through here, and EB would be one of the sides of the four-sided square. Okay? So, here's EB. This would be one side of a four-sided square. We draw it out here. All right. Now, I will tell you more in the next video, so stay tuned.